Hi, welcome to my Lab 5 for physics. I decided to do collision of two baseballs. We try to roll them directly at each other and calculate the energy lost due to friction and deformation. Um, the main idea is that the balls should, in theory, keep all their momentum. Um, However, we do know that's going to lose some energy due to friction. Uh, the model, originally based on the initial data, shows that the ball A, which is this blue ball, would hit the ball and then go downwards, while the red ball or ball B would go up and to the left. However, as you can see, while the ball was rolling, it did change velocities while it was rolling, so it hit at a different angle, leading it to not look like this. Instead, it looked like this, where ball A was rolling to the left, but some part through it starts to kind of increase its velocity in the y direction, and so it hits the ball B at an angle, leading to both of them going their different ways. But this shouldn't be a problem because their momentum should be roughly equal to each other. However, as I've calculated, they are not. So ball A started off at 3 meters a second, negative x direction, and because since both of the balls have the same mass, you can kind of just not get rid of it, but kind of put it as a placeholder so you don't have to calculate it. We also didn't know what the mass of the ball is. So ball's A velocity was negative 0.9 and in the x direction and 1.02 in the y direction, that's meters per second. Ball B was negative 1.19 and in the x and negative 0.34 in the y. Going down to the actual calculation of it, after we can just use the velocities, as I said, because the equation just momentum equals mass times velocity. So we can kind of just smush those two together. So the total or at least the total momentum is negative 2.09. M is just the mass in the x direction, and 0.68 meters times mass in the y direction. And yes, there is momentum in the positive y direction. However, as long as the magnitude of the momentum is the same, all the momentum is conserved. However, as you can see, it isn't. It's missing from the magnitude 0.8 m, or the mass. And that's just for the linear. For angular momentum, because the balls roll, with a diameter of 0.075, the initial angular momentum of the first ball was 0.045. The second ball was, after collision, was 0.02. The first ball was 0.02. The second ball B was 0.15 m. The total difference being, I think there's supposed to be an extra zero right here, but the total angular momentum is 0.039, the difference being minus 0.0385 in angular momentum. So relating to this energy, we kind of ditch some of the momentum, so because we're looking for energy now. So we're going to use kinetic energy translational and kinetic energy rotational. And K rotational, always the angular momentum and the moment of inertia, the radius cancels out, so it usually leaves you with 1/2 mass times velocity squared, or whatever fraction will come out of the moment of inertia. In this case, it's 2 divided by 5, and so dividing by 1/2, it'll lead to 1/5 mv squared. Plugging it into the v into Ke rotational is 0.128 m, still the mass, joules, and Ke rotational or translational, which is just plugging in what v is, using the magnitude of the we're using the magnitude of um, we're using the magnitude of 2.2 here. Um, or wait, no, we're not. We're using the magnitude of zero point 0.8, which is the change in momentum or the change in velocity. That's what we're missing, and that's why what we are trying to find is the missing amount of energy. And so adding together the total energy lost by deformation and friction is about 0.448 mass joules. Here's the what if questions. If balls are hit straight on when they collided, the most ideal situation would be that ball B, the second ball, stationary ball, would get hit and then instantly, not instantly, but basically start moving at 3 meters a second to the left, while ball A, which was the one initially moving, would become stationary. The data was weird, and the reason the data was weird was because the balls aren't perfect spheres. If you know baseball, they have the laces on the edges, so they can definitely roll strange and not perfectly because they're not perfect spheres. See, there's some, and our initial velocity was probably off a little bit because the y component was probably not caught by the tracker, so it wasn't included in the initial. So that's probably why the model was a bit off. Yeah, that's because the balls weren't hit on. They were hit at an angle, which made them go their own different directions.